Alright folks, I just want to take a look at some of these Unit 2 test practice questions. I'm not going to do all of them, I'm just going to kind of jump around to which ones I think are particularly difficult or sort of different looks at some of the stuff we've done to look at. So for this number one, part B is very straightforward, so I'm not really going to hit that. I do want to talk a little bit about part A, however. So we've got a coefficient of static friction. Remember, mu sub s is the static friction of 0.36, and we want to know if our box is going to move. And to determine if it's going to move, we have to look at the maximum force of static friction. So the maximum force of static friction is equal to mu sub s times the normal force. Back that up a little bit. Times the normal force. So when those are equal, it is at its maximum. The force of friction can be anything less than or equal to that, the mu sub s times the force of friction, but when it's equal to, that is the maximum. Erase some of that. So in order to determine if the object is going to move, and we have to do this quite often, whenever we have a problem where it doesn't tell us if it's going to move, we need to start by checking to see if it's going to move. So I'm going to start off by saying the force of friction is going to be equal to mu sub s times the normal force. I can substitute some stuff in there. Go ahead and substitute in the 0.36. And my normal force, I actually have to look and do a little work for that one. My downward force, it tells me the mass is 4.2 times 10 to get me the weight. And because my object isn't accelerating at all in the y direction, I know that my normal force is also going to be equal to 42. These two have to be equal. So 0.36 times 42, and that gives me my maximum force of friction, which is going to be 15.1 newtons. And this is my maximum friction. I could have less than that, but at the most, my friction can take care of 15.1 newtons worth of force. So it says that the tension applied is 9.8 newtons. So my applied force, or my tension force, is 9.8 newtons. 9.8 is less than my force of friction at its maximum, which means that my object does not move. Object does not move. There is not enough force that I'm applying to overcome this maximum. And for most people that is okay, they're comfortable with that. The problem then is if a question asks, what is that force of friction? As long as this is true, as long as the applied force or the force I'm trying to move my object with is less than the maximum force of friction, I should clarify that that's the max. As long as it's less than the max, then my force that's being applied, however much I'm pushing or pulling with, is equal to the force of friction static. Those forces are going to be equal. If my object is stopped, then I don't want it moving around at all. And if I have a force of static friction that was greater than my applied force, then I've got a net force in the opposite direction, which means I'm going to accelerate, I'm going to move, and we don't want that. So that's the key there. Let me pull this down a little bit. It's acting up a little bit. This is the key. As long as this is true, as long as this right there is true, my applied force is less than my maximum force of that static friction, then my applied force is equal to that force of static friction. I just want to talk briefly about this one here. Rank the systems from the one with the greatest value for T1 to the least. So the amount of tension we have depends on how much mass we have hanging from that string. So for A, we have a total of 5m. For B, we have a total of 5m. And for C, we also have a total of 5m. So because all of those strings are holding the same amount of weight, they have the same tension. So they are all the same. We don't have to rank them at all. They're all equal. From greatest to least with T2, I would say that T2 for A is the greatest because it has 4M, and then T2 for C because it has 2M, and last but not least, T2 for B is the lowest. So let me erase some of this stuff. And for T1 for system A, if the system accelerates upwards, that's just working with some of those variables, so that's not too challenging. So this part A is sort of what I was talking about with that first problem, where the force of friction is not the actual maximum force of friction. So it tells us that the block remains stationary. So really we need to find what force is trying to pull down the ramp. We need to find this force. Remember, that's mg sine theta. And that is going to equal our force of friction if the block doesn't move. As long as the block does not move, if we know that the block doesn't move, any force that's trying to move our block, so in this case mg sine theta is trying to pull our block down the ramp, the force of friction is going to match it, but in the opposite direction. So I actually don't need my mu sub s at all. I can say that mg sine theta equals, let me do a little differently here, make it a little more clear. So I've got mg sine theta. More importantly, I've got net force equaling ma. So I've got mg sine theta pulling in the positive direction. I've got my force of friction keeping it in the negative direction. And that equals 0 because my acceleration is 0 because I'm stationary. That whole side becomes 0, which means that mg sine theta does equal the force of friction. And then it's just a matter of substituting. It told me I have a mass of 2.3 times 10 for gravity is going to be 23 times the sine of 18 equals my force of friction. So 23 times the sine of 18 is going to get me 7.1 as my force of friction. 7.1 newtons. Now, had you gone and found the maximum, it would have been greater than that. It would have been, let's see, 23 cosine of 18 to get my normal force, times that mu sub s, and it comes out to 8.75 as the maximum force of friction. But I don't have to use all of that force. My friction is going to be lazy. It's going to do the bare minimum that it can. And it only has to do 7.1 newtons of force to stop my block from moving, and that's what it's interested in doing. So this is an excellent example of a variables type of problem, where it doesn't give us any numbers. It just tells us, hey, we got some stuff going on, do the best you can with it, and write out an expression for F, the amount of force we're applying to our object, in terms of given quantities, and it tells me that I cannot just say normal force. I have to have some other values for the normal force. I have to be more specific with that. So a box of mass M is pushed up a rough incline, so that means I have friction. At a constant velocity, that means my acceleration is going to be 0 by a force F, as shown in the diagram. Coefficient of friction between the surface and the mass is mu sub k. So I'm going to start out with a net force equation. I know that net force equals ma. My mass is whatever it is, but my acceleration is 0, so I can just drop a 0 on that sort of right side. It said that I'm moving at constant velocity. Constant velocity means no acceleration, which means my net force is 0. Other than that, in the positive direction, I've got F, whatever direction I'm moving in. I just like to keep it positive, and it tells me I've got a force pushing in that direction. And then I've also got the force of friction trying to stop that movement. And this is kinetic friction because it said we are moving. It's constant velocity, so we have kinetic friction. The formula for kinetic friction is friction. Pause, I think I got a little ahead of myself. I've got my force, and that is minus mu sub k times the normal force, or capital N as it said down here. But the problem tells me that that is not good enough. It says that n is not a given quantity, and I need to express my answer in given quantities. So if I take a look at sort of a diagram, if I was going to draw this, I've got a normal force pointing up, but then also on the downward direction, we've got mg cosine theta. Mg cosine theta there. And these two, it turns out, are equal to each other. Because I'm not accelerating off of the ramp or into the ramp, or off of the slope or into the slope, those two have to be equal. We've shown that before. So instead, I can then substitute this guy in for my normal force. So the force applied minus mu sub k times mg cosine theta equals 0. And it looks like I've pretty much set up everything I need. I'm just going to rearrange it so that F is by itself. F equals mu sub k times mg cosine theta. Just want to talk briefly about this letter C. What happens is the magnitudes of T1 and T2 if theta were increased but stays less than 90. Both of these tensions would have to decrease. As we increase this angle, this x component gets smaller and smaller. As it goes, there's less pulling in the x direction and more in the y direction, which means that T2 must get smaller to balance that out, to keep it suspended and at rest. As this T1 becomes more and more straight up and down, closer and closer to 90 degrees, it also has to get smaller. The weight does not change. It stays at 150 newtons downwards. The more we tilt this angle upwards, the closer it gets to 90 degrees, the more it is focused in the y direction. Back here where it's perfectly balanced at whatever this angle is, it had to use a lot of its magnitude to pull in the x direction. As we angle it up towards the y, it needs less and less. So T1 also has to decrease there. And much beyond that, folks, the rest of these problems are pretty straightforward. This one is probably the only one that's a little bit more. We'll talk about that one in class briefly, and we've seen examples of those in the notes as well. There's just a little thing we have to do when we've got an accelerating mass on one side. Really, we need the tension for D to equal M1 M1G. The tension pulling up on M1 has to be the same as the weight of M1. So that's the key for D, but other than that, there is not too much else to really go over. These are pretty much straightforward. The rest of the way, pretty easy. We've seen plenty of these before, so I'm not going to take my time up. I'd encourage you to continue working through these. Hopefully they are successful for you. Remember, Thursday we have our test, and tomorrow we will spend reviewing. I'll work through some of these in class or ones very much like them.